All right, so this is lab 14, and I'll probably ask y'all questions as we go along, just so that it's not just me talking the whole time. And also my voice sounds bad, as you can tell. So this Z load, as I discussed earlier, is like a still true load. This is the load that is receiving the power, receiving a current I secondary, and it's going into here, and it's consuming the power that we've sent out. So whenever it asks for Z load, it's put it in a box for us, but we need everything in ohms if we need it in Z. So the first step that we'd have to do in this one is solve for XC, right, which is 1 over 2 pi FC. 1 over 2 pi F is in this statement, 500. C is right there, 0.1 microfarads, and it comes out to 3183 ohms. That is the X of C. So the Z of the C would be negative J, because it's a capacitor, 3183. So this total Z load, in this case, would be 1,000 minus J 3183. If we wanted that technically in engineering units, it would be 1 minus J 3.183 kilo ohms. But usually when you're just like writing the thousands, it's okay to still stick with the 1. So this Z reflected, and this, as I said, the first time that you see a transformer problem, you can just put it all in a box. So let's put it in a big blue box. Everything on this side, right here, this side of the circuit can go into a box. And that box will look like, we'll draw it below, but let's solve for it first. The A is right there, 2 to 1. So A is 2. If it said 1 to 2, that A would be 1/2, right? It's just the ratio, the turns ratio, and remember that's telling us the turns, number of coils inside of these. And you can tell just these turns, this goes from 2 to 1, so there's twice as many coils on the left as there are on the right. That also means there's twice as much voltage on the left side as there is on the right. So A is 2, we just take this formula here, A squared, 2 squared, 1,000 minus J 3183, and I get 4,000 minus J 12,732, and that's all ohms. So now it says to draw it, and this is what I said, almost every time that we have one of these transformers, it's beneficial to draw it. Is there anything in this line up here? Nope, nothing up top. And then inside this box is 4,000, actually I'll undo that real quick. And we'll say 4K minus 12.73K. And then down here, I could put it in a box or I could just draw a resistor in, right? But there isn't, this is modeling, if you will, the internal resistance of the line, so there's 1,000 ohms there. Another way that you could write that would be like 1,000 minus 0J, 1,000 plus 0J, 1,000 angle 0. That would all mean the same thing. It means that inside of here, this is purely resistive. So now using Ohm's law, I have this tiny simple circuit going on down here. What's the voltage? 5 volts. Angle 0, and so our favorite law, Ohm's law, V equals IZ. I equals V over Z. And this is the current on the primary side. So it's in series circuit now. It's the same current coming out of the source, same current going through the transformer, reflected impedance. So V is 5 volts, angle 0. The Z is everything on the primary side. So if I wanted to write it this way, you could also write like V total, Z total, I total, because that's everything on the primary side. I don't prefer to write V primary because that's not V primary. I'm looking at V total because the V primary is what is across this. That's the V primary, but that's not what I'm looking for. I'm looking for the V total. in this case. But I total, because it's in series, is the same as I primary. So Z total is just add those up. So now it's 5K instead of 4K because we add in the 1,000 because it's the Z total. And then that should be minus J12 732. Plug that into the calculator and we get 365 microamps, angle 69 degrees. So now this E primary, what could also be called V primary, is the voltage drop across the reflected impedance, which is also the same as the voltage across the primary windings, which makes sense when we consider equivalence, that we took everything on the right side and we put it in between these two nodes. And so across here is still V primary, also called E primary, right? And that's the same as what we had up here before we put it in a box as E primary. And I should write that as E primary just to be consistent. There we go, E primary. So that's the same after I put it in a box as before, but it's, look how much easier it is to now solve using Ohm's law, V equals IZ, and I can say E primary is equal to I primary Z primary. And that Z primary in this case is that Z primary reflected. Another way, if you wanted to get straight to the E primary, using this circuit above, is you could use voltage divider rule. As it is, we've used 2 Ohm's laws. So we take that 365 angle 69, and that's microamps. Don't forget to put in your times 10 to the negative 6th. And the Z primary is that Z primary reflected, 4K minus 12.73K. E primary comes out to 4.88 volts, negative 4 degrees. So we can use this turns ratio, and it kind of gave it to us on the formula sheet. It actually says A equals I secondary over I primary. And so that's the current on the secondary side of the circuit, and it's just a matter of the turns ratio. Now remember, we said this was a step down transformer because it was going from a higher voltage to a lower voltage, but that means that the current is actually going to go up. And that's just because of the conservation of energy, that the powers on each side of the transformer are the same. And so remember, if P equals VI, well, if the powers, the energy is the same, the conservation of energy means that if V goes down on a step down transformer, then I goes up. So now we can just plug this in. A was 2. And note that I primary is on the equation sheet, it actually does it with absolute values. And so these could be drawn with absolute values. Note that they're not bolded. So I just take the absolute value, which is the magnitude, 365 microamps. So that gives me this portion right here, which is 730 microamps. The angle I don't use in that turns ratio. I get the angle from the dots, right? Angle from dots. And I had this in the concept check. It's either the same angle or it's exactly 180 different. These dots match. They're both up top. Therefore, the angle of I is the same as the angle of the I secondary is the same as the angle of I primary. So the angle was 69, so the angle stays 69. The E secondary, it says using Ohm's law. So we could use Ohm's law again to say V equals IZ. And what we're saying is the E secondary equals I secondary times Z load. I think this is worded a little unclearly. It's telling us the voltage drop across the load impedance. And so the reason why E secondary works is because that is everything that is on that secondary side. If there was a resistor up here, well, E secondary would now no longer be the voltage across Z load, because there would have been a voltage drop, or if there was a resistor down here. But as it is, there's nothing else except E secondary and Z load. So therefore, the voltage across Z load is E secondary. I think that's a little unclear here. Maybe what I'll say is, because what they're asking for, the voltage drop across the load, I think that's poorly written. I think they should, because we're asked to find it with Ohm's law, it could also say Z load, right? So E, the Z across the load, is the I going through the load times the load. Because we're using Ohm's law, that's why I would write it this way. But it says this will be the voltage across the secondary windings, and that is because there's no other elements. There's nothing else taking any power, using any of the voltage, right? It's all E secondary is Z load in this particular circuit. So because of the way they're having us solve it, the E secondary is that. So I can rearrange, or I load is the I secondary, 730, that's microamps. 730 microamps, angle 69, times the Z load, which was 1,000 minus J 3183, right? Double check that. Yep, 1,000 minus 3183 was the Z load. Plug that in the calculator, and I get 2.44 angle -4 degrees. That's volts, 2.44 volts. And that makes sense when I look up above and see that it was 4.88 -4. I could have easily solved for that with the turns ratio, because the turns ratio is A, 2. So it would just divide that by 2. It was a step down transformer, went from 4.88 down to 2.44. The dots match, so the -4 degrees matches the -4 degrees.